looking at what happened if you change the objective function coefficients, right? I'm going to use this problem from the book. Parring here, they make golf bags. So they make some standard bags S and some deluxe bags D. They want to maximize the profit from making the bags. So $10 for standard and $9 for deluxe. Making the bags needs resources. It needs some cut and dye time, and you have 630 hours. It requires some finishing labor. You have 708 hours. It requires some inspection time. You have 135 hours. So those are the constraints. And to solve the problem graphically from last week, you create 2 points from each of your constraints, right? And then that allows you to plot each of the constraints. So there's my finishing constraint over here. There's my inspection constraint over there. There's my die constraint over here. Then you indicate which side of the line you need to be on. In this problem, you need to be on this side, you need to be on that side, and you need to be on this side. So that leaves us to everything in the shade here will satisfy all the constraints, right? You're on this side here, you're on that side, you're on that side. And so that's my feasible region. To find the optimal solution, I have to plot my objective function. I put in 2 objective function lines. In this problem, you see that the direction of increasing z is this way. So moving as high as you can go, point 3 is over there, is the optimal solution, right? So that's the graphical procedure to solve the problem. Before I go on, any question on the graphical procedure to solve the problem from last week? Okay. So now we're going to do some set analysis. So it says, okay, what is the range of the objective coefficient for the standard bag? So that would be this 10 here. For the point 3 to remain the optimal solution. So basically, this can increase or decrease a little bit, and point 3 will be optimal. But how much can it go up or down? And I'll just give you a little motivation over here. So when you start changing the 10 over there, the objective function slope is going to start tilting, right? This way or that way, right? And you can see as long as you don't really go beyond this here, or don't go below this here, then 3 is still going to be optimal, right? If you go below this here, you can see that you can shift higher to 4, right? And on the other side, if you kind of go steeper and beyond this guy here, then you can see you're going to want to move out to whatever this over here is, right? So as long as you're in this zone, then 3 remains optimal. So the question is, you know, how high or low this can go for you to be still in the zone, right? Okay, so we're going to do part A over here. So for part A, the objective function is Z is 10S and 9D. Now we're going to analyze changes to the S here. So I will write it as the coefficient for the standard bag times S, and then 9D. So what we're looking for over here is what is the range of this CS, how high and low, right? Is it 5 to 9, 7 to 11, whatever it is, for my point 3 to remain optimal. Okay, so that's what we're looking for in this sensitivity analysis. So to do that, we'll roughen the graph. Okay, so we'll roughen the graph over here. there's this one over here, and then we have one over there. And then there's one over there. Okay, so there's my standard bags here. There's my Alex bags over there. This was my finishing over here. This is my cut and die over here. This is my inspection line. And then I had my quarters in the problem, 1, 2, 3, 4, 5. And then I have my objective line passing to 3. And as I indicated, you can, as long as it's kind of, not tilting and flying in that zone, then 0.3 is optimal, right? Now we can also calculate and put the slopes in, and I'll show you how to calculate them in a second, but the cut and die constraint has a slope of -7/10. Finishing has a slope of -3/2. The objective has a slope of -CS/9, right? And the inspection, we don't really need it because you can see it doesn't do anything, right? We just want it to be between finishing and CD, right? Apparently, Canvas is up and running again. Other universities are using it again. I heard that U of T has hired a third-party independent company to kind of assess whether whoever attacked their Canvas has planted any kind of worms or virus before we allow students and staff to start using it again. Maybe somebody's watching too many James Bond movie, I don't know. But probably safe than sorry. Okay, so step 1 is we find the slopes that's relevant. So that would be the finishing, the objective, and the CD. So we find the objective slope. So the objective function was Z is equal to CS times S plus 9D. And we see that D is on the y-axis over here. And so we would rewrite the equation in terms of D, because D is on the y-axis. So this has the form of equation y is a plus bx. Here y is d, and then x is s. And so b then would be the slope, right, of the line. And so using that, we can see then the slope of the objective is this distance, right? And that's how I got over here minus CS over 9. Then we find the slope of finishing and cut and die as well. So from the problem, the finishing constraint S plus 2 over 3D 708. again, rewriting in terms of D, we get 1062 minus 3 over 2s, and so we can see that there's my finishing slope right there. And that's what we have over here on the graph, right? Then finally, we'll calculate this cut and die slope here. And we see the cut and die equation is 7 over 10s plus d is 630. And so solving, I get d is 630 minus 7 over 10s. And so you can see the cut and die slope is minus 7 over 10 as labeled in the diagram. Okay, so we find the relevant slopes, and then now we've gotta ensure that, you know, it is in this range. So you need it to be flatter than the finishing line here, and you need it to be steeper than the CD line there, right? Question 1 in assignment 1, I was originally gonna put it on the midterm test, but I thought maybe it'll be a little too hard. So you could see how it goes when you try it. Okay. Then step 2 is, well, looking at the graph. For 3 to remain optimal, we want to be in that zone, right? So we want the slope of the objective to be flatter than the finishing line. And on the other hand, we want the slope of the objective to be steeper than the cut and die line. I shouldn't say I thought it would be too hard, but I thought maybe it might be a little confusing, and then I would have so many students asking questions for clarification, and probably not a good idea on the midterm. But either case, it's not an easy problem, that question 1. Okay, so just so that we can compare slopes, we can need a little reference over here. So maybe your slopes are negative, and a more steep slope would have a bigger negative number. Okay? It would have a bigger negative number. You can have constraints that are upward sloping, and then in that case, a more steep slope will be a more bigger positive number. Okay, a more steep slope has a more negative number, and if the slope were positive, the constrained slope were positive, then a bigger number would have a steeper slope, right? Okay, so now we got a little reference diagram here. We can start making comparisons. So for A, we want objective flatter than fin. So objective is minus CS over 9. Finished is minus 3 over 2. We want flatter. So greater than or less than? Flatter. Greater than or less than? Less than is incorrect. So this is flatter than this. This number is bigger than that. Right? This is flatter than this. This number is bigger than that. So it should be bigger than. Okay, so get rid of negatives. Move this here. Move that over there. And then finally, 9 times, oops, there's no more negative. 9 times 3 is 27. 27 divided by 2 is 13.5. So CS has to be smaller than 13.5. Then for condition B over here, objective steeper than CD. Objective is this, and CD is minus 7 over 10. So steeper, less than or greater than? Less than, right? This is steeper than that, more negative than that, right? So again, put this there, put there to get rid of the negative stuff. And finally, 9 times 7 is 63, divided by 10 is 6.2. Okay, so we can put the two together, and so final answer for the range 6.3 to 13.5. 0.3 is optimal. I have no idea why somebody would target an education learning system, you know? Yes?
Where do you get the CS over?
The CS over 9? There. So what does this range mean in terms of our original problem? It tells me that as long as this here is between 6.3 and 13.5, then 3 here will be optimal. So as long as this here is between 6.3 and 13.5, 0.3 here will be optimal. That's because this between 6.3 and 13.5, this objective slope lies between these two constraints. Okay, it says what is the range of the coefficient for the standard bag for say 0.2 over here to be the optimal solution. Now 0.2 is a little different. 0.3 you have two constraints passing by it. 0.2 there's only one constraint passing by that. So we're interested in what is the range of CS or 0.2 to be optimal. With these questions, you always have to look at your graph to kind of compare. And you can see from the graph, in order for 0.2 to be optimal, the objective slope here has to go steeper than this finishing line. Because if it goes steeper than this finishing line, then you're gonna want to move out to 2, right? So just from the graph, we see that 2 is optimal if the objective is steeper than the finishing. Okay, there's objective, there's finishing, steeper. All right, less than or greater than? Steeper, so less than or greater than? Less than, right? more steep, more negative. Again, move this there, move that there, and so on. And you get CS is bigger than 13.5. But will there be an upper limit like this, right? Will there be an upper limit like that one? Well, you're gonna have to kind of look at the graph here. So as CS gets bigger and bigger and bigger, the objective slope, which is equal to minus CS over 9, is 1 million, 10 million, so it becomes minus infinity, right? But you can see that you still have a tendency, even becomes fully vertical in minus infinity, you still have a tendency to move out, all right? So 2 is still the optimal solution, okay? But from graph, 2 is still optimal. And so, the range, as long as CS is bigger than 13.5, there's really no limit on that, and we see 0.2 optimal. Now the test, if you don't put something here, I'm going to assume you don't know what you're doing, and you're going to get marks deducted, okay? So you have to indicate, you know, if there's a range or not, right? How about 0.4? So what is the range of CS for 0.4 optimal? So that's your little in-class exercise here. Okay. So 0.4 is that one, right? Yes?
What's the upper limit, sorry?
Infinity. Yes?
My question was, why are we using the equal in the inequality? Wouldn't that just be the other lines then? Because we're saying the objective, the slope needs to be between the lines. Or
Well, when it's equal, then what it means is you have multiple optimal solutions, and both 0.3 and 4 will be optimal. But technically, 0.3 is still optimal, right? Okay, so I will put up this graph, and then you can figure out the range of the coefficient for the 0.4 to be optimal. You know, I don't think the university knows that you can access Purpose through the mobile app. Because there's a big kind of problem right now. A lot of professors don't keep a spreadsheet of marks separately from Kirkus. So if they cannot get in Kirkus, they are unable to calculate the student's final mark put on Rosie. And so some graduating students are not graduating. So they're trying to figure out what to do. But if they know there's this back door, why don't you just get on it, right? So anyway, maybe I should tell them. Okay, range CS 0.4 optimal. I'll go around in case you got some questions. Yep.
它现在
E
不长高，但是它比较更平。
is on the y
2的话
axis.
它是要更平。
So if I solve this problem and I had s on the y-axis, then I would rewrite my equation in terms of s. Yeah.
你看它上来了。
We're back on 3, right? Now on the other hand, if it goes farther than this INS here, then you're gonna wanna move up to 5, right? So you have to be in this zone, right? So once again, looking at my graph. So from the graph, 4 is optimal if objective is flatter than the CD. Also, the objective needs to be steeper than the inspection. Okay, so we meet those two there. Now, A, we have everything. Objective, we already have. CD, we already have. Flatter means a bigger number, right? Flatter is a bigger number. So, bigger. Move this there, move that there. And then 9 times 7 is 63, divided by 10 is 6.3. Okay, so we need that. B here, we don't have the INS slope, so we need to determine that first. From my original problem, the inspection constraint is 110S, 1/4 D, 135. And then rewriting in terms of D is 540 minus 4/10 S. And so I can now get my inspection slope. Okay, so now that I got my inspection slope, I want objective steeper than INS. There's the objective. There is the INS. Steeper, more negative number. And solving, I get 3.6. Put the two together. I get the range, 3.6, 6.3, 0.4, optimal. So we start by looking at the graph so that we know what we need to compare with. And then if you don't have the slope yet, then you need to calculate it. And in order to make the comparison, and then you just put the two together. Right? Any question on that? Yes?
On A, shouldn't we put the equality if we're dividing on
I moved this over there, moved over there, so I don't have equal, so I don't have negatives.
A? Oh.
Anything else? Okay, then one more for you, the final point. What is the range of CS for 0.5 optimal? Okay, so let you try one more here. Now put back the big picture. So we want 5. Diagram again. For this to be optimal, the objective slope has to go kind of flatter, right? So now you have a tendency to move up to 5, right? The objective slope has to come a little flatter, so now you have a tendency. Because if it goes steeper than this, then you're just back and forth, right? So the objective has to be flatter than this inspection in order for this to be optimal. So once again, looking at the graph, uh, 0.5 optimal if the objective slope is flatter than INS. So we have all the numbers we need. There's objective, there's INS, flatter is less of a negative number. And so solving, I get CS is, needs to be smaller than 3.6. But once again, is there like a lower limit of some kind? So we see that CS becomes more and more, it can, drops from 3.6, maybe drops to 1, maybe drops to -5, -11, -1,000,000, and so on. So CS becomes very negative. the objective, slope, becomes, which is minus CS over 9, becomes, positive infinity. So what does that look like on the graph? We see that it starts out, the slope starts out being negative, right, downward sloping. And then as CS becomes negative, it turns to become positive. But you still have a tendency to move out to 5. And as CS becomes more and more negative than minus infinity, you still have a tendency to move out of 5. Okay, so there's no limit, right? So as CS becomes minus infinity, the objective slope becomes kind of positive infinity, right? But you still have a tendency to move there. So it starts like this, and then it becomes positive and going out there. It becomes more and more vertical, and you're still going out there. And even fully vertical, you're still going out there. But we can see the point is still optimal. So range is minus infinity CS 3.6. Okay, any question on that one? Now, how about if we make changes instead to the log spec? Instead we make changes to the log spec. So what is the range of the coefficient for the deluxe bag for the original 0.3 to remain optimal? What's the range of the coefficient for the deluxe bag for the original 0.3 to be optimal? So what is the range of the coefficient of the deluxe bag for 3 to remain optimal? So we have to rewrite our objective now in terms of the deluxe bag. So we put the 10 back on there, but we change this as the coefficient for the deluxe bag. So we're looking for what is range for this for 3 to be optimal, right? And just as before, if you want 3 to be optimal, the objective slope has to be between flatter than fin and steeper than CD. Except, of course, the objective slope is no longer this, but you have to, recalculate it. But we want it to be here, right? So we want the objective slope flatter than fin, and we want the objective slope steeper than CD. But we need to recalculate the objective slope. So the new objective is this. And because D is on the y-axis, we have to still rewrite it in terms of D. Okay, so we still rewrite it on D because D is on y-axis. And so we now get the new objective slope is defined as minus 10 over CD. So a lot of students get confused this is because they think that we're analyzing changes in D, we need to rewrite it in terms of S or something. But again, whatever's on the y-axis, you have to put it like that. Okay, so now we're ready to make the comparison. So call this A, call this B. Okay, objective flatter than fin, so objective is now this. Finishing was as before, flatter is less of a negative number, and so you get CD needs to be bigger than 20 over 3. Then for B, objective is steeper than CD, there's your objective. There's your CD line. Steeper is more negative, and so you get CD needs to be smaller than 100 over 7. And we simply put the two together. And so for range, 20 over 3 and 100 over 7, 0.3 optimal. Okay, so you see the way to analyze changes in the D variable is the same. All right, I need to go get my laptop and set up Lingo. If you haven't signed in, please sign in over here. I have lecture notes from the 2 classes from last week if you want to have a look.